You should never mess with the idea of parallels. I've been through that endless night myself. A night so dark, it took away every ounce of light and joy from my life. I beg you, stay away from the science of parallels. But of course humans are curious by nature. Imagine two trains racing side by side, the metal groaning with pressure, bolts straining as each engine fights to inch ahead. It's neck and neck, then something unbelievable happens. The two trains crash into each other. Metal crumples like paper. Flames erupt. The crowd gasps in shock. But how is that even possible? The tracks were parallel. And by definition, parallel lines never meet, no matter how far you extend them. So what went wrong? This question has haunted mathematicians for centuries. One of the first to seriously think about it was Euclid, the legendary Greek polymath often called the father of geometry. His book, Elements, is one of the most influential texts in the history of mathematics. In it, he laid out 5 basic postulates, or rules, about geometry. The 5th postulate is about parallel lines. It essentially says that if 2 lines are parallel, they'll never intersect. The other 4 rules were quickly proven and accepted. But that 5th one? It remained unproven for nearly 2,000 years. And then, in the 19th century, something shook the foundation of everything we thought we knew. Mathematicians discovered that maybe it wasn't proven because it simply couldn't be. Maybe parallel lines could meet after all. This changed everything. Suddenly, Euclidean geometry wasn't the only system anymore. Space itself could bend and twist in ways we never imagined. A Hungarian mathematician was among the first to challenge Euclid's postulate. He had seen the dark side of this idea and warned others never to follow his path. But why does this even matter outside of abstract math? The truth is, this concept is deeply tied to one of the most important questions in all of cosmology. A question that astronomers are still trying to answer today. To uncover the truth, we'll travel through strange and mind-bending universes, places where light bends in circles, where you can see the same galaxy multiple times in different directions. We'll explore folded space where, if you look far enough, you might even see yourself looking back. We'll dive into realities where parallel lines meet over and over again. This journey may break your sense of logic, but it will reveal something profound about the universe we live in, and perhaps even help us understand which universe we live in. So what's the big question we're chasing? If the universe is expanding, what exactly is it expanding into? On December 27, 2024, a telescope in Chile spotted something that triggered a global alarm. For the first time in history, the United Nations activated its planetary defense protocol. What did they find? An asteroid, catalogued as 2024 YR4, about the size of a football field. If this asteroid hits Earth in 2032, it could release energy hundreds of times more powerful than the Hiroshima bomb. But will it actually hit? When stories like this break, especially in science, they're often surrounded by drama and exaggeration. That's why it's crucial to check your sources. I rely on ground news when researching events like this. They helped make this video possible by offering a simple way to see how different outlets report the same story. For the asteroid 2024 YR4, Ground News pulled together over 220 articles in one place, comparing headlines, bias, and factual accuracy. For example, a low-rated source ran with a dramatic headline, "Graphic shows asteroid the size of a football pitch on course to hit Earth." But more reliable sources clarified that the chance of impact is actually only about 1 to 2%. If you want to stay fully informed on science and more, visit ground.news/hotu or scan the QR code. Use my link for 40% off their Vantage plan, the same one I use every day. Let's get back to the cosmos. In medieval Naples, Pope Innocent IV lay dying. His forces had just been crushed by Manfred, the King of Sicily. Some historians believe this devastating news led to the Pope's death just days later. But others whisper of something far more mysterious. A ghost. Not just any ghost, one belonging to a little-known English bishop named Robert Grosseteste, with whom the Pope had clashed many times. Grosseteste lived in the 13th century and eventually became the Bishop of Lincoln in England. He was outspoken and driven, calling for reforms that put him at odds with both the Pope and King Henry III. But beyond church politics, Grosseteste made groundbreaking contributions to early science. He believed in something radical for his time, the idea that experiments could uncover the hidden rules of nature. And he had a special fascination with light. He was the first to correctly explain how rainbows form through the refraction of light. But Grosseteste's vision went further than that. He used light to explain the origin of the universe itself. In his view, the universe began when light burst out from a central point and expanded outward, gradually forming matter. This was more than 700 years before modern scientists would propose a similar idea. Today, some even call him the Big Bang Bishop. Grosseteste died in 1253 and was buried in Lincoln Cathedral. Stories of miracles began to surround his grave, and many in England treated him like a saint. But the Vatican never made it official, possibly because of those lingering rumors that his ghost had murdered the Pope. Still, his cosmic vision remained buried for centuries, until another man of the cloth picked up the thread. In the early 20th century, a Belgian priest named Georges Lemaitre revived Grosseteste's idea. Lemaitre barely survived both world wars, first as an artillery officer narrowly escaping a gas attack, and later when the Americans accidentally bombed his house. Despite all that, in 1927 he published a groundbreaking paper solving Einstein's equations of general relativity. These equations describe gravity on a cosmic scale. Others had solved them before, like Karl Schwarzschild, who used them to describe black holes. But Lemaitre's solution was different. It suggested that the universe was expanding. Most scientists ignored him. Even Einstein dismissed the idea harshly, saying, "Your calculations are correct, but your physics is abominable." Einstein himself tweaked his own equations to force a static universe. But the evidence for Lemaitre's idea had already started to surface. In 1915, American astronomer Vesto Slipher had noticed that galaxies seemed to be moving away from us. He discovered this by measuring something called redshift. Here's how it works. First, you take light from a galaxy and break it into a spectrum, just like Grosseteste understood when he described how raindrops create rainbows. Then, you look for dark lines in the spectrum where certain colors are missing. These lines correspond to specific chemical elements in the galaxy. If the lines are shifted toward the red end of the spectrum, it means the galaxy is moving away. The more redshift, the faster it's receding. This was only half the story. The missing piece came in 1929, when Edwin Hubble measured the actual distances to those galaxies. When he compared distances with redshifts, he found a clear pattern, now known as Hubble's law. The farther away a galaxy is, the faster it appears to be moving. Modern measurements say it's about 23 kilometers per second for every million light-years. That sealed it. Lemaitre was right. The universe is expanding just like Grosseteste imagined centuries before. So, if the universe is expanding, what does that really mean? Let's make it easier by connecting it to something more familiar, a loaf of bread. Imagine a simple raisin bread. You mix the dough, knead it, and set it in the oven to bake. Over time it rises, expanding in size. Now picture yourself as a tiny raisin inside this dough. As the bread rises, you'll notice something interesting. Every other raisin is moving away from you. A raisin that was just 1 centimeter away will now be 2 centimeters away. It's not running away from you, it's just being carried along as the dough expands. Now take this idea further. If another raisin was originally 2 centimeters away, by the time the bread has finished baking, it would be 4 centimeters away. That means it seems to be moving at 2 centimeters per hour. If it was 3 centimeters away, it would end up 6 centimeters away, an apparent speed of 3 centimeters per hour. So what's going on? The further away something was from you to begin with, the faster it appears to move away. But it's not because the raisins are zooming through the dough, it's because the dough itself is stretching, increasing the distance between everything embedded within it. This is exactly how the expansion of the universe works. Hubble's law tells us that galaxies appear to be moving away from us, but in reality they're not flying off through space like rockets. What's actually happening is that space itself is expanding just like the dough in our raisin bread. And just like with the raisins, the farther away a galaxy is, the faster it seems to be moving away. It's not because something is pushing it, it's simply because more space lies between us and that galaxy, and all that space is stretching over time. This doesn't mean new space is being created out of nowhere. No extra space is magically popping into existence. Instead, it's the existing space that's being stretched. This stretching is allowed by the laws of general relativity, which tell us that space and time aren't fixed or rigid. They're flexible, dynamic, and ever-changing. It's a concept that took a long time to become mainstream, but now it forms the foundation of modern cosmology. And once you accept it, many of the most confusing cosmic phenomena begin to make a lot more sense. One of those phenomena is redshift, the same thing that astronomer Vesto Slipher observed over a century ago. As light travels across the expanding universe to reach us, the space it's moving through stretches. This stretching pulls on the light waves themselves, making them longer. And since red light has the longest wavelength in the visible spectrum, this stretched-out light appears more red than it would have when it was first emitted. The more the universe has expanded during the light's journey, the more redshifted that light will be by the time it reaches us. And this leads to another mind-bending twist. People often ask what happens to the energy of this stretched-out light. After all, energy can't just disappear, right? Isn't that a fundamental rule of physics? Well, yes, at least under most circumstances. According to classical physics, energy can't be created or destroyed. It's a law we've all learned in school. But in an expanding universe, that rule doesn't always apply in the same way. When space itself is changing, the rules that govern fixed systems no longer hold up. In other words, energy conservation doesn't apply universally when the universe itself is in motion. Take redshifted light again. As the light waves stretch, they lose energy. So if you catch light that traveled through billions of light years of expanding space, it will contain less energy than it did when it began its journey. The photons lose energy simply because of the expansion. This may seem counterintuitive, but it's one of the key features of our universe. It challenges our classical understanding of physics and forces us to rethink what we mean when we talk about fundamental laws. The universe, it turns out, doesn't have to obey our old rules in every situation. There's another fascinating consequence of all this. The most ancient light that has traveled across nearly the entire history of the universe, doesn't just arrive redder and weaker. It also takes longer to get here than we might expect. That's because the space it had to travel through was expanding all along the way. The light didn't just have to cross a fixed distance, it had to chase a moving finish line. And as a result, the events that happened in the early universe appear to unfold in slow motion when we observe them today. They evolve 5 times more slowly than similar events would if they happened now. So we know the universe is expanding, but when did it start? When did this stretching of space begin? If the universe is getting larger today, it must have been smaller yesterday. And smaller still the day before that. If we keep rewinding the cosmic clock, going back hundreds, thousands, even billions of years, we eventually reach a point where the universe was incredibly tiny. Keep rewinding further and we reach a moment where all the matter, energy, and space we now see was packed into an unimaginably dense and hot point, a singularity. This is what we call the Big Bang. The term Big Bang can be misleading. It makes it sound like there was some kind of explosion, a huge blast from a central point. Naturally, people ask, where exactly did this explosion happen? Where is the center of the universe, the place the Big Bang came from? But here's the thing, the Big Bang didn't happen in one spot. It happened everywhere all at once. It wasn't an explosion in space, it was an explosion of space. If the Big Bang created the universe itself, then asking where it happened is like asking where in a room an explosion occurred when the explosion also created the room itself. The room didn't exist before the blast. And here's a curious detail. Everyone, no matter where they are in the universe, sees the same expansion happening around them. From our viewpoint on Earth, it looks like everything is moving away from us. But an observer in a galaxy 10 billion light-years away would see exactly the same thing. They would think we are the ones moving away. That's because there is no special center. The expansion is uniform, it's happening everywhere to all of space at once. That's why it's so hard to visualize and so easy to misunderstand. We're not at the center. No one is. The expansion is not from somewhere, it's from everywhere. This brings up another classic question. If the universe is expanding, what is it expanding into? The answer to that is even more complicated. People assume there must be some kind of outer space, some bigger container that the universe is growing into. But that's not how it works. Space itself is what's expanding, not inside anything else. There is no outside of the universe in the conventional sense. Asking what the universe is expanding into is like asking what's north of the North Pole. It's a question that breaks down because of how we define space and direction in the first place. And to truly understand that, we have to explore the shape of the universe. Picture flying above the surface of the moon. You see jagged mountains, ancient craters, and wide, empty plains untouched by anything except a few human footsteps. It's a landscape of cosmic history. Many of the moon's craters are named after legendary scientists, Einstein, Hubble, Slipher, and Lemaitre to name a few. And among them are 2 names that lie on opposite sides of the moon, both literally and figuratively, Minkowski and de Sitter. These 2 physicists proposed very different visions of what the universe might actually look like. Hermann Minkowski once taught Albert Einstein, though their relationship was rocky. Minkowski famously called Einstein a lazy dog who never bothered about mathematics. Despite that, Minkowski contributed a lot to our understanding of space and time. He imagined a universe that was flat, though in science, flat doesn't mean two-dimensional. It means a universe with no overall curvature. One that goes on infinitely in all directions without looping back on itself or closing like a sphere. His ideas laid the groundwork for understanding space-time as a 4-dimensional entity, 3 dimensions of space and 1 of time, all fused together. Wilhelm de Sitter had a different approach. He came from a long line of lawyers but chose to pursue the laws of the cosmos instead of the court. When he died in 1934, the New York Times praised him as not just a scientist, but an artist who saw the cosmos taking shape in his equations. De Sitter imagined a universe where the geometry of space was very different. His models described a universe dominated by the repulsive force of a cosmological constant, a mysterious energy embedded in the fabric of space itself, causing it to expand faster and faster over time. These two models, Minkowski's flat universe and de Sitter's accelerating one, are not just abstract concepts. They represent real, testable possibilities. And which one turns out to be correct determines the ultimate fate of the universe. Will the cosmos keep expanding forever, gradually fading into a cold, dark emptiness? Or will it slow down, stop, and perhaps even reverse, collapsing in on itself in a big crunch? Or maybe the expansion will continue forever, but at an ever-accelerating rate, tearing galaxies, stars, and eventually atoms apart in a scenario known as the Big Rip. All of these depend on the shape of space and the nature of the energy driving its expansion. It is the late 1780s. The United States of America is still a newborn nation, and far across the Atlantic, a German philosopher named Immanuel Kant is pondering a question that continues to echo through physics even today. What is space really? Is it a container, a stage upon which all events play out? Or is it something more abstract, perhaps a set of relationships between objects? His ideas were revolutionary at the time, challenging the idea that space must exist independently of the matter within it. This line of questioning, strange and philosophical back then, now lies at the heart of how we understand the expanding universe. Because if space itself is growing, then we're not just moving within it. The distances between objects are stretching. It's not like dots on a balloon being pushed apart. The balloon itself is inflating. This is a subtle but crucial distinction. The galaxies aren't flying through space like projectiles. Instead, the very fabric of space between them is swelling. And here's where it really starts to bend the brain. If space is expanding everywhere, including between galaxies billions of light years apart, what's it expanding into? It's tempting to imagine the universe as a bubble, growing into some larger empty void. But that's not quite right. Because that larger void doesn't exist, not in any physical sense. Space isn't expanding into anything. Rather, space is being created within the universe itself. There's no edge we're growing toward, no outer shell we're pressing against. We often use visual metaphors like the surface of an inflating balloon to help make sense of this. But remember, those are just models. They don't include the third dimension that we live in. The surface of a balloon has no center on the surface itself. The center exists in a higher dimension. Similarly, our universe may be expanding without having a central point within the universe from which it expands. That's why asking what the universe is expanding into can sometimes be the wrong question. It's expanding, yes, but not into anything in the way we'd imagine expansion here on Earth. So when astronomers describe the expansion of the universe, they're describing changes in the distance between objects over time, not motion through a static void. And this subtlety has massive implications. For instance, two galaxies could be perfectly still relative to each other and yet still drift farther apart simply because the space between them is stretching. It also means that the edge of the observable universe isn't a wall or a boundary. It's just the limit of how far light has managed to travel since the Big Bang, given the age of the universe and how fast space itself has been expanding. And this leads us into one of the strangest, most mind-warping consequences of all. If the universe really is infinite, then that means there's infinite space behind us, ahead of us, and in every direction. But due to the finite speed of light and the age of the universe, we can only ever observe a limited volume. That observable slice, the cosmic horizon, represents a bubble around us 93 billion light-years across, beyond which we can't see. Not because there's a wall, but because the light from beyond that region simply hasn't had enough time to reach us. And here's where things get eerily poetic. Because every observer, no matter where they are in the universe, will see their own observable bubble, centered around them, extending out to their own horizon. There is no true center of the universe, not in a physical sense. Every point can be considered the center of its own observable universe, making each one both unique and completely unremarkable. It's a concept that elegantly dethrones our cosmic ego. Now, if the universe is infinite and continues endlessly in every direction, that might seem to resolve the question of expansion. But remember, we still don't know for sure if that's the case. It may look flat to us, and it may behave like an infinite space, but we've only ever observed a finite portion of it. That leaves the door open to the possibility that beyond the edge of what we can see, space could curve back on itself, or twist in ways that defy our everyday understanding. That's why topology is such a fascinating subject in cosmology. Not just because it allows for weird and wonderful shapes like the 3 torus or the Hansch-Went manifold, but because it gives us the tools to ask, what kind of infinite, or finite, space do we really live in? And perhaps most remarkably, we're actually starting to probe these questions with real observations. The search for repeating patterns in the cosmic microwave background continues. Some astronomers have even proposed ultra-sensitive missions designed to scan the sky for these subtle signatures. If they ever do find repeating patterns, if the same cluster of galaxies appears in multiple parts of the sky, it would be the strongest hint yet that space wraps around on itself. But so far the cosmos has kept that secret well. And while we wait for those answers, we must sit with the strange, unsettling truth that we may never know what lies beyond the limits of our observable universe. Our tools are powerful, our theories sharp, but we remain creatures confined to a tiny corner of spacetime, trying to piece together an unfathomably vast and complex puzzle. A puzzle whose pieces are still falling into place, guided by light that's traveled for billions of years, whispering the story of creation in the faintest possible tones. And yet, even from those whispers, we've built models that stretch to the edges of time and space. Perhaps we will never know if the universe is truly flat or infinite. Perhaps we are forever trapped in a hall of mirrors with no way to find the edge. But that won't stop us from trying. Because even when the answers remain just out of reach, the pursuit itself takes us farther than we ever dreamed. America hasn't even hit its teenage years yet. Over in France, a storm is brewing that will soon erupt into a bloody revolution. The streets will cry out for change, and before long, King Louis XVI will find himself facing the sharp and merciless edge of the guillotine. But elsewhere in the world, far from the turmoil, a young boy named Carl Friedrich Gauss is quietly seated in a German classroom. He's just a schoolboy, listening carefully as his teacher assigns a task. Add up the numbers from 1 to 100. It's the kind of problem meant to keep students busy, tedious, repetitive, and dull. Yet within seconds, young Gauss calmly announces the answer, 50-50, sir. His teacher stares, speechless, as if struck by lightning. It's said that the teacher's jaw dropped faster than the blade of the guillotine in revolutionary France. While it's unclear whether this event actually happened or is just another legend, the tale has become one of science's great origin myths, like Archimedes running naked through the streets shouting Eureka, or Newton's supposed apple-induced epiphany under a tree. Real or not, it highlights Gauss's extraordinary mathematical intuition at a very young age. The cleverness behind Gauss's solution lies in a beautiful insight. He realized that you don't need to add the numbers one by one. Instead, you can pair them. 1 with 100, 2 with 99, 3 with 98, and so on. Each pair sums to 101. There are exactly 50 of these pairs, and 50 times 101 equals 5050. It's a brilliant shortcut that a child figured out in seconds. A moment that captures the essence of mathematical genius. Whether true or not, the story has endured because it perfectly illustrates how Gauss's mind worked. Gauss would grow up to become one of the most significant mathematicians in history. In fact, many consider him the most influential of all time. His work wasn't just about equations on paper. It helped build the very framework through which we understand the universe. It laid the mathematical foundation for how we describe cosmic expansion, and even challenged our understanding of space itself. Earlier we talked about how the universe is like raisin bread rising in the oven, or like galaxies stuck to the surface of an inflating balloon, visual metaphors that try to explain cosmic expansion. But these analogies have limits. Whether it's dough in an oven or a balloon in a room, they're all expanding into something. Our universe, according to modern physics, doesn't expand into space. It is space and it's expanding. To truly grasp this mind-bending idea, we have to dive into the strange, fascinating world of mathematics known as differential geometry. And that brings us right back to Gauss. This branch of math helps us understand how things can curve and stretch, not just in our 3 familiar dimensions but beyond them, into places our minds can barely imagine. Let's start small. Picture a flat sheet of paper. Now roll it into a cylinder. To do that, you had to bend it through a 3rd dimension, one that exists outside the paper itself. Mathematicians call this surrounding dimension the embedding space. If our universe were shaped like that cylinder, and astronauts were navigating its surface, they could draw a giant triangle and still find that its internal angles add up to 180 degrees, just like on a flat sheet. From their perspective, the cylinder feels flat. Only by stepping outside and looking at it from the embedding space would they see its curve. This kind of shape is said to have extrinsic curvature, curvature that's only visible from the outside. But from within, it's indistinguishable from flatness. That's because a cylinder has no intrinsic curvature. And here's where Gauss made his mark. In 1827, he published a groundbreaking result that revealed how to measure this kind of curvature from inside the shape, without needing an outside view. It was called the Theorema Egregium, or remarkable theorem. It showed that some shapes, like a cylinder, can be curved extrinsically but still be flat intrinsically. Now compare that with a sphere. When you walk across the surface of a planet or the moon, you can detect its curvature without ever leaving it. The angles in a large triangle on a sphere add up to more than 180 degrees. That's how you know you're on a curved surface. This property, being curved from the inside, is called Gaussian curvature, named in honor of Gauss's revolutionary work. His theorem proved that while you can map a sphere onto a 2D surface, like a flat piece of paper, you'll always introduce some kind of distortion. You can't flatten the Earth without warping it. That's why every map you've ever seen is lying to you in one way or another. The most common world maps, like the Mercator projection, preserve angles, making navigation easier. But they skew areas badly. Greenland, for example, looks almost as big as Africa, even though it's 14 times smaller. Other projections, like the Lambert cylindrical equal-area projection, do the reverse. They preserve area but distort angles. Thanks to Gauss's Theorema Egregium, we know there's no perfect map. You always have to trade something. But what happens when we move beyond spheres and cylinders to the shape of the entire universe? To find out, we jump forward to 1857. A 76-year-old Gauss is in the audience as one of his former students, Bernhard Riemann, delivers a lecture that will change everything. Riemann had once planned to study theology but ended up under Gauss's mathematical wing at the University of Göttingen. Gauss admired Riemann's creativity and once praised his gloriously fertile originality. In his famous lecture, Riemann proposed a radical extension of Gauss's ideas. What if you could describe the geometry of spaces with more than 3 dimensions? That's exactly what he did, creating a powerful new framework called Riemannian geometry. Riemannian geometry introduced one of the most important ideas in all of modern science, the geodesic. This is the shortest path between 2 points on a curved surface. On a globe, for example, a geodesic isn't a straight line on a flat map, it's a curved arc called a great circle. That's why planes flying from London to New York actually head north, not south. Though it looks curved on a map in 3 dimensions, it's the straightest route. And in an even more bizarre example, a plane can travel in a straight line from Alaska to India, without ever crossing land, yet look completely bent on a 2D projection. These strange truths are central to Einstein's general theory of relativity. Einstein realized that space and time aren't separate, they're woven together into a 4-dimensional fabric called spacetime. His former professor, Hermann Minkowski, was the first to coin the term. But to describe the curvature of this 4-dimensional reality, Einstein couldn't rely on Gauss's 3-dimensional geometry. He needed Riemann's more flexible mathematical framework. Riemannian geometry became the backbone of general relativity, the theory that replaced Newton's old idea of gravity as a force with a new concept, gravity as the warping of spacetime. According to Einstein, objects like the sun don't tug on planets with invisible strings. Instead, their mass bends the spacetime around them, and Earth simply follows the natural curve of that distortion. It's not being pulled, it's rolling like a marble in a funnel. And here's the wildest part. In 4 dimensions, the Earth's path around the sun isn't curved. It's a straight line. Just like that London to New York flight, the curvature we see is only a shadow of a straighter path through a higher dimension. We only think it's curved because our view is stuck in 3 dimensions. This concept becomes especially vivid when we observe gravitational lensing. When light from a distant galaxy passes near a massive cluster of galaxies, its path appears to bend, creating warped, magnified, or multiple images. Riemannian geometry lets scientists calculate how much the spacetime is curved by the mass of the cluster. And when they do the math, they often discover a troubling fact. There's far more curvature, and therefore far more mass, than what we can see. That extra mass? We can't see it, touch it, or detect it directly. But it's there. Astronomers call it dark matter, and it might just be the key to understanding the hidden structure of the cosmos. To its use of Riemannian geometry, general relativity can completely describe spacetime, our universe, and its expansion in terms of intrinsic curvature alone. This is a profound shift in understanding because, within this framework, there is no need for an external embedding space, and consequently, no requirement for the universe to be expanding into anything. But as you might expect, this isn't the complete story. Just because the universe doesn't need to be expanding into anything doesn't necessarily mean that it isn't. This subtle difference opens up numerous fascinating questions and theoretical explorations about the very nature of our existence, the structure of spacetime and the boundaries, or lack thereof, of the universe itself. This mystery of what the universe might be expanding into becomes all the more intriguing when we consider the vastness and complexity of space exploration. Take, for instance, the 7 months it takes for NASA's Perseverance rover to travel through the solar system. After those long months of travel, it is the next 7 minutes that will ultimately decide the rover's fate. Hurtling through the thin Martian atmosphere at nearly 20,000 kilometers per hour, it appears from the surface like a giant shooting star lighting up the Martian sky in broad daylight. The parachute opens, fluttering as it stabilizes, and the rover rig emerges from its protective chrysalis. Stabilized by a series of thrusters, it is suspended mid-air, dangling on long puppet-like wires from the sky crane, the final piece of technology responsible for safely depositing the rover on the surface. As the rover lands, the sky crane powers away to avoid contaminating the pristine Martian environment, specifically the Jezero crater, which the mission has traveled almost 500 million kilometers from Earth to explore. Landing a car-sized rover on a distant planet is no small achievement. Yet this mission also carries another equally impressive milestone: the deployment of a miniature helicopter named Ingenuity. This small aircraft would go on to make history by completing the first powered flight on another world, a feat previously thought impossible. Despite being designed for only 5 flights, Ingenuity defied expectations and completed a total of 72 flights, far surpassing its original mission parameters. This achievement highlights the extraordinary possibilities of modern technology, but it also underscores a fundamental truth about the forces at play in our universe, particularly gravity. Despite the weight and mass of an entire planet like Mars, this tiny aircraft, with a fuselage no bigger than a tissue box and weighing no more than a bag of potatoes, could lift off and climb more than 20 meters above the dusty Martian surface. This remarkable feat was only possible because of Mars' weak gravity, which is approximately 1/3 of Earth's. Gravity, despite being one of the 4 fundamental forces that govern the universe, is also one of the most mysterious and least understood. This paradox is particularly striking when we realize that gravity is the force that most directly impacts our daily lives. Its effects are easy to observe, from the way objects fall to the ground to the sensation of weight that anchors us to Earth. And yet, despite being foundational to our experience of the world, gravity remains a puzzle. To grasp the enormity of this mystery, consider the gravitational attraction between 2 electrons. This attraction is 100 tridecillion times weaker than the electromagnetic repulsion between the same 2 particles. A tridecillion is a number so vast it's hard to even conceptualize. It's 1 followed by 43 zeros. This massive difference in strength between gravity and the other 3 forces, electromagnetic, weak and strong nuclear forces, poses a significant problem in physics. Physicists believe that in the early moments after the Big Bang, all 4 fundamental forces were unified into a single all-encompassing force. As the universe expanded and cooled, these forces separated from one another in the briefest sliver of time, only fractions of a second after the Big Bang. Already, there is solid evidence that the electromagnetic and weak forces were once a single force known as the electroweak force. The strong nuclear force shares similar properties to the electroweak force, suggesting that they too were once unified in the very early universe. However, gravity remains stubbornly separate, described by Einstein's general theory of relativity, which, as we've discussed, doesn't integrate well with the quantum field theories that describe the other 3 forces. This disparity between gravity and the other forces raises the question: if all 4 forces were once equal, what happened to cause gravity to become so much weaker than the others? A potential answer lies in a theoretical branch of physics known as the brane world. This concept introduces a mind-bending idea of an embedding space that seems straight out of science fiction. According to braneworld theories, the 4-dimensional spacetime we experience is merely a surface, or brane, within a higher dimensional hyperspace known as the bulk. To visualize this, imagine dropping down a dimension. Picture an ant crawling around the surface of a hollow sphere floating in midair. The ant is confined to the 2-dimensional surface, the brane, while the rest of the space, what it cannot see, is 3-dimensional. Similarly, we could exist on a 4-dimensional brane embedded within a higher dimensional bulk, potentially with more than 5 dimensions. This fascinating idea stems from string theory, which attempts to unite gravity with the other fundamental forces by positing that all particles are made up of tiny vibrating strings. These strings vibrate in different ways to produce the variety of particles observed in nature. String theory's importance extends beyond just understanding particles. It also gives insight into the forces that govern those particles. A special class of particles called bosons are responsible for carrying forces. For instance, the electromagnetic force is mediated by the photon, a boson, while the strong force is mediated by gluons. Physicists have experimentally verified the existence of the bosons responsible for 3 of the 4 fundamental forces, but the graviton, the hypothetical particle that would carry the force of gravity, has yet to be detected. This elusiveness of the graviton is one of the key puzzles in modern physics. If it does exist, the graviton could hold the answer to why gravity is so much weaker than the other forces and provide us with crucial information about the true nature of space and the universe's expansion. Within the brainworld theory, string theory distinguishes between 2 types of strings: open strings and closed strings. Open strings, which are tethered at one end to a brain, can only interact within the confines of that brain. Closed strings, however, which form a loop and are effectively tethered to themselves, are free to move throughout the entire bulk. The graviton, believed to be made of closed strings, would thus be able to travel through both our brain and the bulk. This could explain why gravity appears to be so much weaker than the other forces. As it leaks into the higher dimensional bulk, its strength is diluted, while the other forces remain confined to our 4-dimensional brain. Testing this theory is challenging, but physicists have proposed several experiments that could provide indirect evidence of gravity leaking into the bulk. For example, particle collisions at the Large Hadron Collider could create gravitons, which might escape into the bulk, leaving detectable gaps in the data. Another possible test could involve updating the famous 18th-century experiment by Henry Cavendish, which measured the gravitational attraction between 2 metal spheres. In our familiar 3D world, forces such as gravity follow the inverse square law, meaning that the gravitational attraction between 2 objects decreases with the square of the distance between them. But if gravity is leaking into a 5th dimension, its strength would diminish faster than expected, following an inverse cube law instead. This would mean that, over the right distance, gravity would fall off more quickly than predicted, and astronomers would be able to detect the deviation. However, no such deviations have been observed, and such experiments would need to be conducted with increasing precision. If scientists were to observe a deviation from the inverse square law, it wouldn't be definitive proof that gravity is leaking into the bulk, but it would raise exciting new questions. Perhaps gravity is leaking into extra dimensions that are part of the universe itself, curled up and hidden from view. Only further research and perhaps more sensitive experiments will help confirm whether or not the higher dimensional bulk exists, and if it does, what it could mean for the nature of the universe's expansion. Another concept from string theory that may help answer some of these questions is ADS/CFT correspondence, a groundbreaking discovery that links the laws of quantum physics with the geometry of higher dimensional spaces. Proposed in the late 1990s by physicist Juan Meldacena, ADS/CFT correspondence connects the physics of a higher dimensional anti de Sitter space, ADS, with the quantum field theories that govern particles on the boundary of that space. This correspondence provides a framework for understanding how gravity might work in higher dimensions, with the potential to resolve the long-standing puzzles of quantum gravity and unify the fundamental forces. However, the correspondence is not perfect. It relies on the assumption that the universe is like an anti-de Sitter space, and while this idea has intrigued physicists, it is still far from being universally accepted or proven. The holographic principle, which underpins ADS/CFT, also suggests that all the information about our universe might be encoded on a lower dimensional boundary. If this is true, then everything we observe in our 3D universe could be a projection of information from a distant 2D surface. This possibility leads to mind-boggling questions about the nature of reality and the limits of human perception. Could the entire cosmos be a hologram, a projection of a deeper reality? While it is difficult to test this hypothesis, the mere thought experiment challenges everything we think we know about the universe. As we have seen, gravity is perhaps the most enigmatic of the 4 fundamental forces. The theory of general relativity suggests that spacetime is curved by mass and energy, and that this curvature drives the expansion of the universe. Yet the deeper we dive into the mysteries of gravity, the more we realize that there is still much we don't understand. Should higher dimensions exist, they may be key to understanding why gravity is so weak compared to the other forces. Whether or not we will ever prove the existence of these dimensions, one thing is clear: the search for answers to what the universe is expanding into, and what lies beyond the observable universe, will continue to drive the boundaries of scientific exploration. In conclusion, the questions surrounding the expansion of the universe, the nature of gravity, and the possibility of higher dimensions.